I will present some work on error correction. Let's start with some motivation. So we are in the quantum error correction picture, and what we do is we encode our logical information in a code space, which is the common eigenspace of some commuting operator that we call stabilizers. Then, in order to detect errors present on the system, we measure these stabilizers, and what we obtain is a classical bit string that we call syndrome. This syndrome, importantly, contains all the information we need in order to perform correction. And in fact, this protocol works as long as the syndrome is error-free. This is, though, far from reality, and noisy measurements often that occurs. So to tackle with the problem of noisy measurements, there are two main strategies. The first one is to repeat measurements over time and use the whole syndrome history in order to perform correction on the syndrome. The second one is the so-called single-shot approach, where we use just one round of noisy measurements in order to perform correction. In this case, we don't ask to completely wipe out the error from the system with one round of correction, but what we want is to keep the residual error on the system under control over time. The main advantage of this work is that it doesn't require time overhead and is resilient against time-correlated noise. As the title suggests, our work focuses on the single-shot approach, and is in fact a work on two parts. The first part is some foundational part, where we ask whether there exists or not a set of minimal sufficient conditions that ensure that a code has single-shot properties. To this end, we propose the definition of confinement. The second part is the study of a family of codes, the 3D homological product codes, of which, for instance, the 3D toric code is part, and we assess their single-shot behavior numerically, achieving record results. This scheme is also the outline of the talk. I will first then introduce our theoretical results and then our numerical simulations. Let's introduce some notation we're going to use throughout the talk. So by E, we indicate any poly error on the code space, and by sigma, the syndrome extraction function. So since we allow for the syndrome to contain some noise, we are going to consider a noisy syndrome, so a classical bit noise string SE. We consider two noise models, the adversarial noise model and the stochastic noise model. In the adversarial setting, we assume that errors are always correctable, meaning that their weight is upper bounded by the code distance. In the stochastic noise setting, instead, we assume that errors can have arbitrary location, but the probability of any error to occur is decreased exponentially with its size. Let's now introduce our concept of confinement. So the confinement is a relation from between the weight of the error and the weight of the syndrome. To understand what confinement is, we can think about the 2D Ising model, which is not a full error correction code, but is enough to understand how confinement works. So if we put a qubit on faces and a stabilizer on edges, so that errors are highlighted in gray, then we see that the syndrome, in this case, is given by the boundary of the error region. And so for errors of weight low enough, what we have is that the relation between the weight of the error, the gray area, and the weight of the syndrome, which is the perimeter, is the same relation that is between the area and the perimeter of a polygon. So there exists a function that relates the weight of the error and the weight of the syndrome. Nothing is said, and we don't impose any condition between the relation from high weight errors and their syndrome. More formally, we say that a code has TF confinement if for all error of weight at most t, their weight is upper bounded in this way. Since we are interested in a good family of codes, we will ask that the integer t grows with the length of the code, and f is the same polynomial across the whole family. Our definition of confinement is similar to the one introduced by Bombin in this paper, or the robustness property for expander codes here introduced. The difference, though, is that whether here they allow just for linear confinement function, we let f to be any polynomial. Our definition of confinement is justified mainly by these three theorems. So we first prove that confinement is in fact a sufficient condition for a code to be resilient in the single-shot setting to adversarial noise. We then focus on 3D homological product codes and prove that they have confinement for phase flip noise. And last, we prove that anytime the confinement function is linear, this is enough for codes to have a single-shot threshold, so to be resilient to stochastic noise in the single-shot setting. To prove that confinement is a sufficient condition for single-shot, we use a two-stage theoretical decoder that we call shadow decoder. So to understand how it works, let's first define what a t-shadow of a code is. So it's just the image via the syndrome map of the set of poly operator of weight at most t in the code space. So we have in particular that the 2 shadow of a code is containing the 5 shadow of the code, and so on. Let's now suppose that some error occur on the code space which correspond to a syndrome, but some of the measurements go wrong, and so we fed our decoder with a noisy syndrome of these 4. The first step is the syndrome repair step, where we take our syndrome and we find a minimum syndrome recovery operator that maps our input syndrome in the tau shadow of the code. Then we found the minimum weight qubit operator that explains the syndrome. And what we have is that in general we will have some residual error on the system, which is simply given by the original error plus the recovery operator. And what we find is that whenever the code has confinement, we are able to bound the residual error, the weight of the residual error, with a function of the weight of the measurement error. And this is enough to prove that in the adversarial noise setting, confinement codes are single shot, because whenever we are able to control the weight of the measurement error, we are able to keep under control the residual error too. By using a variant of the shadow decoder and some result in percolation theory, we are also able to prove that whenever the function f is linear, this relation yields to a threshold for the code. We will not detail this proof here, and we will switch to the 3D homological product codes. So the 3D homological product codes are a family of codes built starting from the homological product, which is just a recipe to build CSS codes starting from 3 matrices, in the case of the 3D one, of classical codes. So we take 3 parity check matrices and we build a spacing using tensor product in this way. So we obtain a chain complex, a level structure like this one, where we can make a correspondence between object of the code, so Z stabilizer, qubit, and deck stabilizer, and basis vector in each space. We see that we also have a layer that is not needed by a CSS code, but will give the code some redundancy for the X stabilizers. What we prove is that we can embed any 3D homological product code on a cubic lattice. So we are going to draw an edge for any vector in this space. So we're going to draw a transversal edge for any vector in this first space, a vertical one, and an horizontal one. Then, if we overlap these 3 lattices, what we find is a cubic lattice like this one, with possible some missing edges. So for instance, here a row of vertical edges is missing. in this picture, Z stabilizer corresponds to vertices with support highlighted in red, and X stabilizer corresponds to faces with this support of 3 kinds. And what is important is that whenever the seed matrices have some locality property, these are preserved under this identification. And in this way, we're able to give an explicit proof that the 3D toric and surface code are in fact part of this family. As I said, we show that these codes have confinement, and to see how this is the case, we can think about the dual lattice of the one I just presented, where we put then qubit on faces and X stabilizers on edges. And then, with a reasoning similar but a bit more involved to the one that we have seen for the 2D Ising model, we found that these codes have qubit confinement. As I say, our proof for stochastic noise in the single shot setting works only if the confinement function is linear. And we have seen that 3D homological product codes have a qubit confinement function. So we assess their single shot behavior with some Monte Carlo simulation. So qubit will experience a phase flip with probability P, and stabilizers are flipped with probability Q equals P. We then use a 2-stage decoder, which is different from our theoretical shader decoder, because the first step is a syndrome repair step, which uses some redundancy in the syndrome to correct it, while the second step just solves the corrected syndrome problem. In our implementation, we chose to use either minimum weight perfect matching or belief propagation plus order statistic decoding for the first step, and BP plus OSD for the second step. Since some error is always present on the system in the single shot setting, we need a way to assess the performance of our decoder. And to this end, we use the concept of sustainable threshold that has been introduced in this paper. So what we do is we simulate n round of qubit noise and noisy measurements, and followed by a last round of noisy-free syndrome extraction and correction. We then compute the threshold of this correction procedure, and we define the sustainable threshold as the limit of this quantity for the number of rounds that goes to infinity. Under this assumption, we first benchmark our decoder against with the toric code. Here in this table, we indicate with, again, single-shot decoders and with a clock decoders which uses the whole syndrome history. Our result is highlighted in blue, and we can see that both in the case of noise-free syndrome and noisy syndrome, we obtain the best results in the table. We also benchmark our decoder on the 3D surface code, again obtaining a threshold at around 2.9, and also on a random family of 3D homological product code using BP plus OSD for both decoding steps, finding a threshold at 2.7%. To sum up, what we have found is that confinement is in fact a sufficient condition for a code to be single-shot in the adversarial setting. And more, to date, no code is known to be in this black region here. So no code is known to have single-shot property for adversarial noise, but do not have the confinement property. We conjecture that confinement in general, superlinear confinement, is enough for a code to exhibit a threshold, and we prove this in the case of linear confinement. We support our conjecture with some numerical simulation using BP plus OSD and a 2-stage decoder, achieving record results.